I welcome you all to the quantum mechanics class after a long time, almost 3 months, and I wish that and pray that this COVID-19 to be finished soon and we resume our classes at university. But for the time being, for our online classes, I have designed my own blackboard and we will continue our classes just like as we did on a whiteboard. So it will be almost a class environment and I will appreciate your feedback on the channel. The very first thing that we covered was in the previous lecture was the section 2.3, the harmonic oscillator. We started with the Schrodinger wave equation and we considered this potential. We have discussed in much detail that why we are selecting this potential. Today I will discuss it a little bit more and then we will go to the algebraic solution. In the previous lecture we have also done the algebraic solution, but the first edition of Griffiths, it was having some limitations, and that's why in the second edition Griffiths changed those calculations or the way he has derived the solution of the wave function. So we have covered the first edition in the earlier lecture, and in this lecture we will go on with the second edition of Griffiths, and I will tell you that where is the mistake in the first edition. So let's start with this, that we considered our potential to be half kx square, and then this k we replaced, as you know, that it's like a spring that we are having an atom, and this atom is attached to another atom like a spring. So this is attached on all direction, and the quantum harmonic oscillator is one of the very important topic, that whenever we are having oscillation around a center position, then we approximate the calculation with the help of the quantum harmonic oscillator. Now, the classical harmonic oscillator can have any energy, while the quantum harmonic oscillator is having some set of quantized energies that we will derive. The potential that we have selected, like V equal half kx square, which I have discussed in the previous lecture, that why we are taking this one. Another reason for this one, if I consider this situation, then one atom will go closer to another atom, and if this is the distance r between the atoms and this is the potential, which is a function of r, then we know that this potential is like this, and as the atom goes closer to each other, there is more attraction, and then after a certain distance, this is, let's say, r naught, from this equilibrium distance we are having a repulsion between the atoms, and the potential become repulsive after this point. So in this range we are having the attraction increases and the attraction become more and more negative here, and this is the maximum attraction between them. When the distance decreases, then the equilibrium distance, then repulsion starts here, and this is approximated, the potential is like a parabolic potential, and this is the equilibrium distance that we have, and this potential is actually like x square. So that's why we have selected this half kx square, and we will now find that in this region quantized energies exist, and we will derive with our calculations. So here in the algebraic method I will rewrite this equation, and this equation is that we know that there a momentum operator we write minus IH bar and d by d x. If our wave function is only a function of x, then I can write it as a derivative instead of partial derivative, and I can put in here in this equation, so I can write that this will be p square by 2m and plus half mv square plus half and m omega square x square, and this whole will be then operated on a psi, and this will be equal to E psi. Now I can write this in short. If I take 1 over 2m as common, then I can write this as p square plus, and as I have taken m common here, so this I can write m omega x whole square, and psi equals E psi. Now we will have to solve this equation, and to solve this equation we will use the algebraic method, and inside the algebraic method I know that u square plus v square I can write is iu plus v multiplied by minus iu plus v. Now u square plus v square, we can write it like this. In the first edition, we have utilized the same tactic, but this tactic is true for numbers only. We cannot apply it on p in x, because p in x, this is a momentum operator and this is a position operator, and when we will write px and xp, then they are different. So we cannot apply this thing on operators. We will have to calculate operators differently, and that is the mistake which is done in the first edition, that we have gone with this one for the operators as well. So in the second edition, Griffiths has rectified this mistake and he has calculated for the operators as well, because if I find this commutation relation, then this is px minus xp, and this is not necessarily 0 for most of the operators. So they do not commute with each other, and this is equal to non-zero, it is equal to something. While when we calculate this for numbers, for u and v being two numbers, then this thing will always be equal to 0. So we will have to rectify this mistake here as well. Now I can write this one as 1. I can write means when I factorize this one, I can write p plus means ip plus this one and minus ip and this one. So I can write that, let's say for the plus symbol, I write that a plus is equal to 1 over 2m, and here I write that this is minus ip as per this equation, minus ip plus m omega x, and a minus I write 1 over 2m and plus ip minus plus ip, so plus m omega x. Now for convenience means this has been factorized and this is equal to E psi, but for convenience I am writing one extra term here, and that extra term is that if I write h bar omega here inside this square root, then my calculation will become easier, and I will tell you in a while that what's the benefit of writing h omega over here, because this h omega, if I write this equal h omega, it will come here. So for this ease, for this convenience, we have written, means h omega is written for convenience. So we have written this h omega just to ease our calculations. So I can write them in a compact form is a plus and minus is equal to 1 over 2 m h bar omega, and here I write minus and plus ip plus m omega x. Now the very first thing that I want to calculate is to calculate that what will be the product of a minus with a plus. So this will be, I will write, when these two will multiply, this square root will go, and we will have 1 over 2 h bar omega, and then for a minus we will have, means a minus we will have plus ip plus m omega x, and for the other we will have minus ip plus m omega x. Now do multiply them. As we know here, I, m and omega, they are the constant here. I, m and omega, these are actually the constants, and we can shuffle them here and there, while p and x are actually the operators, so we cannot shuffle their orders. So let's go on with this, that a minus a plus will be equal to 1 over 2m h bar omega, and here the very first, these two will multiply, and we will have the ip multiplied with the minus ip, so minus, and then I square again minus, so we will have plus p square, and then plus, this will be I, and then the constant m omega, and then the operators p and x, so they will be in the same order. Similarly, plus, this will multiply with this, and it will be minus I m omega, so this will be minus I m omega, and then xp, this will multiply with this, and it will be simply m square omega square x square. So we are having this, and then just writing this thing, so 1 over 2m h bar omega and p square plus m square omega square x square, plus we will have to take common this p and x from here, so m square omega square x square, and then take minus I m omega is common, so it will be xp, and then this will become minus and px, and this will be the final form. Now we will have to see this thing is they are operators, whether this thing is equal to 0 or not. So we will have to sort this thing out. This is actually a commutation relation. Any two operators A and B is equal to AB minus BA. If these are the two operators and they commute, then we will say that this is equal to 0 for operators when the two operators commute with each other, and this will be equal to non-zero when they don't commute. So commutation we will discuss later, but commutation is actually when the measurement of one operator disturbs the system for